Previously, we were applying Newton's second law of motion to equilibrium situations where the acceleration was equal to 0. Here we're going to change our tack and look at the more general case where the acceleration of the object is not equal to 0. We call that dynamics in distinction from equilibrium. And I think it's probably best to just do a few cases here by example to show how this goes. So in the first case here, I'm going to take a look at an elevator. And let's say the elevator is heading upward, but it is slowing down. So just as a real quick check, if it's heading upward but slowing down, which way does the acceleration point? Yeah, it points downward. And to make it concrete, let's say the magnitude of our acceleration is 2 meters per second squared. Alrighty. Now let's say that inside our elevator we happen to have a scale. So there's a scale. And that's the little top on it. And then we'll stick on the scale a 10 kilogram mass. What I would like to know is what number reads on the scale. Now so that gets into the important question of what is it that a scale reads? Well, a scale reads is the normal force. So let's go ahead and do a force identification diagram for our mass here. And we can see that our only contact force will be the normal force. And that's what we're looking to find. And then long-range forces, all we've got is gravity. Okay, so now that we've done our force identification, let's go ahead and draw a free body diagram. So it'll turn out that typically, in a case like this, it's actually maybe slightly more convenient to put the plus y-axis downward, but to show why, I'm going to do this example, making it upward. Not that it's a big deal either way. Almost more a matter of personal preference, as we'll see. So, all right, here is, I've collapsed my weight down to, or my mass down to a single geometric point. And so I'll now go ahead and draw in the forces. Whoops. So we'll have the normal force pointing up that we don't know how much it is. And we have the force of gravity pointing down, which we do know how much it is. It's equal to m times g. Alrighty. So now with that, we can go ahead and apply Newton's second law to the situation here. So Newton's second law, as we're using it right now, is F net equals ma. So we can go ahead and write out our forces as vectors here. So we'll be adding the normal force and gravity to get ma. Now what we'll do is we'll take this vector expression and we'll break it into x and y components. So in the land of x here, we see that there's literally nothing pointing in the x direction. So the object isn't, it doesn't feel any forces in the x direction, and we already worked out that it's accelerating downward, so there's no component of acceleration in the x direction. So we literally get nothing useful here, which is fine. All right, so now we go and take a look at the y equation of motion. Let's just go with the standard choice that you might intuit to do, which is to make up positive here. So then we first look at any positive, any forces that are pointed in the positive y direction or have pieces in the positive y. In this case, the entirety of the normal force points in the positive y direction. So we'll just write n. And then the entirety of gravity points in the negative y direction. So again, like before, we'll write minus Fg, and the minus sign to account for it pointing downward, equals m. And now here we gotta be careful. The acceleration points down. And so with the acceleration pointing down, that means that the y component of the acceleration is actually negative a, like that. So we could have chosen, and in a later problem we will choose, to put plus y downward. And if we did that, it would flip the order of these and make this a positive a, which would be the same thing as taking this equation, multiplying both sides by -1, but you're less likely to forget to take this into account. So it's a matter of personal preference. If you're, if years and years of math classes have just burned into your brain that plus y has to point up and plus x has to point to the right, then go ahead and roll with that. But the cost of that will be that sometimes you'll have to add these minus signs to account for the fact that the actual acceleration is pointing down. Okay, so with that, what we're trying to solve for is the normal force, so we can rearrange to get the normal force on the left. So this will be add Fg to both sides, Fg, distribute the negative sign over, minus ma. Then we can go ahead and put in our model of gravity, which is m, but the force of gravity is equal to mg, so this will be mg minus ma. So finally we get that the normal force, so the number that's actually going to be read on the scale will be equal to m times g minus a. So we can put that in, that's 10 kilograms, times 9.8 newtons per kilogram, minus 2 meters per second squared. All right, so kilograms cancel kilograms, leave me with newtons, that's good. Kilograms times meters per second squared is the same thing as newtons, so that's good. Both terms are going to give me newtons, and when I crunch it through, I find that the scale reads 78 newtons. All right. For our second example here, we're going to take a look at a system known as Atwoods Machine. Atwood was a scientific demonstrator from around the end of the 19th century, Scottish. And he found that just this system here of taking a pulley, so I'm just hanging a pulley from the ceiling here, run a string off of it on each side, a couple of masses. He found that you could rework this problem over and over and over and over again using many different methods. And so it's sort of become a classic teaching example. So we'll start off here first by making the pulley massless. And let's go ahead and say that mass 1 is 0.1 kilograms and mass 2 is 0.2 kilograms. Now, what we're going to want to know is what is the acceleration and what is the tension in the string. All right, so to that end, first thing we want to think about is, well, how is this going to accelerate? When I let the masses go, we know from practical experience the big one's going to go down and the small one's going to go flying up. So we'll say that the acceleration of the big mass, m2, is going down. The acceleration of the small mass, m1, is pointing up. Next question. You'll notice that I wrote both of them as a, suggesting that the acceleration is the same. And in fact it is. These are magic physics land strings which don't stretch. And even with real world strings, after they stretch a little bit, it'll be the same difference. So why can we say the acceleration is the same? Well, it's easier to say, what if it wasn't? Let's say the acceleration of this one was bigger than the acceleration of that one. Then that would mean with each second, this one would cover more ground than this one, which would force the string to stretch. But we're assuming we're at a point where either it's an ideal string that never stretched in the first place, or it's a real world string that has already completed its stretching. Either way, the string's not going to stretch. So the only way we can have the string not stretch is if the two accelerations are the same in magnitude. Obviously, they differ in direction. So this sort of reasoning in physics speak is called exploiting a constraint. Here, because these are constrained to move the same amount of distance in the same amount of time, they will always have to have the same acceleration and the same velocity. And because the pulley is massless, we'll be able to say that the tension in the string on either side is the same. Now, showing this, I'll have to defer it a little bit in full rigor until we get to Newton's third law of motion. But if we consider that with a real-world string, it would have stretched a little bit. The force due to tension the tension in the string will be proportional to how much each bond between atoms in the string stretched. And the amount of stretch you'll have as you're going over the pulley is the same as anywhere else. So by that logic, the tension is the same. I'll be able to argue this more rigorously after we've visited Newton's third law of motion. But for now, I'm just going to ask you to say, yeah, this seems like a very reasonable thing. And it is. Okay. So we've got two unknowns here, which means we're going to need two equations. And at first you might think, well, Newton's second law will give that to me because I'll have x and y. But again, it's going to turn out here that all the action is going to happen vertically. So we're kind of stuck there. We can't write one Newton's second law expression, but we can write two Newton's second law expressions, and that'll be fine. What we'll do is we'll treat M1 as one of our free bodies, and we will treat M2 as our other free body. So now we've done two force identification diagrams. So for mass 1, we'll take a look at, and the circle cuts through the string, so that's tension. And then for our long-range force, we have the force of gravity, which we'll call Fg1, because since it's a less massive object, the force of gravity on it will be less than for mass number 2. All right, then same deal here. This circle cuts through the string, meaning we'll have a force due to tension. Then we're identifying long-range forces. We'll call this one the force of gravity 2 for mass number 2. And this is again because they aren't equal to each other. All right, so now let's go ahead and draw free body diagrams for each of these. So for system number 1, the red system, we will have the force due to tension pointing up, and we will have Fg1 pointing down. And for system number 2, the blue system, it's going to be the exact same deal. We'll have the force due to tension up, and we'll have Fg2 down. Let me make this a little more explicit here. I'm trying to draw it so that Fg1 is shorter than tension. There we go. Now these two forces due to tension are the same magnitude. And I'm going to indicate that by just throwing a slash through each of them, just to remind me that they're the same. When we get to Newton's third law, we'll find out that this notation has a little more significance than that. But for the moment, we're just saying it's all due to the same force of due to tension in the string. All right, now while we're at it, let's go ahead and identify which way these things are accelerating on our diagrams. This one's accelerating up, and this one is accelerating down. So what's going to be convenient here is for each free body, we are allowed to choose a coordinate system. So for this free body, I'm going to choose the plus y direction to point up. And for this free body, I'm going to choose the plus y direction to point down. Now, why am I doing that? I'm doing that to match the direction, the plus y direction, with the acceleration. This will mean that when I put the y component of the acceleration for each Newton's second law statement will be positive. This allows me to avoid possible arithmetic errors. Now, it will be at the cost of having to realize here that FG2 is positive and the tension here is negative, but that's okay. So with that, let's go ahead and write down Newton's second law for each of our systems individually. So for system number 1, the net force on object 1 will be equal to its mass, m1, times its acceleration. So this will be t plus fg1 equals m1a, like so. And just like before, the x component doesn't give us anything useful because all the action is happening in y, so we'll take the y component. So t points up here, which is the plus y direction for system number 1, so it makes that positive. Fg1 points down, so it's the minus y direction for system 1. So we'll say minus Fg1 equals m1a, and that's because a points the same way as plus y. Okay. And now let's go ahead and do this again, but we'll do it for system number 2. So now for system number 2, we can write F net for object number 2 is equal to its mass, m2, times its acceleration, a. Keep in mind these a's are, I should technically be writing a1 and a2, but since we worked out the magnitudes are the same, I'm calling them both a because we're going to go into components real quick anyway. So just writing the vector sum, this will be tension plus Fg2 as vectors equals m2a. And now we can go ahead and take the y component of that to get, well, here the tension now is pointing in the negative y direction. So I have to write minus t. Fg2 is pointed in the plus y direction, so I'd be writing plus Fg2. And this will equal m2 times a. All right, so now from here it's a matter of turning the crank. I'll go ahead and solve first for the acceleration. And I can do that pretty quick with a trick where I just add the equations together. So I'm going to take this equation here, t, and there are other ways to do this, and if you prefer those ways, this is fine. I'm just showing a way to do it. T minus Fg1 equals m1a. Then I'm going to write here this equation, negative t plus Fg2 equals m2a. Now what I'm going to do is I'm just literally going to add the two equations. Now by doing this, I can go here and say t plus a negative t. That just gives me 0. Now what have I got here? I've got Fg2 is positive, Fg1 is negative, so we'll write that as Fg2 minus Fg1 since I added the two terms. These are both positive, so I'll write m2a plus m1a, like so. All right. Now from here, I can go ahead and substitute in my model of gravity, m2g minus m1g. So that's m2a plus m1a. So now from here, I can go ahead and pull out an a. So I'll write this as m2 plus m1a. And I can pull out a g from here, so I'll write this as m2 minus m1g. Now I can rearrange this for what a is equal to. A will be equal to m2 minus m1 over m2 plus m1 times g. All right. So we'll go ahead and stick in the numbers and see what we get. And what we get is 0.2 kilograms minus 0.1 kilograms over 0.2 kilograms plus 0.1 kilograms. And G is 9.8 newtons per kilogram. But remember, dimensionally, that's the same difference as meters per second squared. So we'll go ahead and make that substitution here to get that it is, that it is 3.27 meters per second squared, which squares with our common sense. It's less than 9.8 meters per second squared, which makes sense. We're not in free fall. We're having to lift the lighter mass, so it makes sense that it's going to be less than 9.8. Now we can go back here and look at the equation, and we can also check to see, does this make some sense intuitively? We could imagine making M2 super big compared to M1. Well, if that's the case, then it doesn't really much matter if you add M1 or subtract M1. You're going to end up with basically 9.8, which makes sense. If M2 is like really big compared to M1, it's functionally almost no different than if you just dropped M2. And if M1 and M2 are equal, you get 0, which makes sense. If you had them at rest and let equal masses go, they're just going to sit there. So it kind of all checks out. Now we're not quite done. We do need to go back and solve for the tension, since we needed that. So we'll just take we'll go back and reuse our Newton's second law expression for system number 1. We could have totally used the one for system number 2. We get the same answer. So T equals Fg1 plus M1A. So this will be M1G plus M1A. So we end up, if we pull out an M1 from everything, M1 times G plus A. So this is 0.1 kilograms. Whoops. Kilograms times 9.8 newtons per kilogram plus 3.27 meters per second squared from before. So give me 1.31 newtons. Now the force of gravity on the object would have been just 0.98 newtons. So the tension is greater than the force of gravity, which makes sense because it's accelerating upward. Alrighty. So at this point right here, just as a final note, there are other ways you could do this. You didn't have to add the two equations together. Any method of solving simultaneous equations that you prefer will work. You could have taken this first equation here, solved it for t. You could have taken the second equation, solved it for t, set the other sides equal. Or you could have solved, say, this one for t and substituted into the value for t there. No matter what you pick, you'll end up with the same expression at the end. And so you'll get the same result. So you don't have to do the algebra this way. You can do the algebra whatever way makes sense for you. This is the way that I prefer, and I just put it out there in case you hadn't seen it that way before. Alrighty, so going forward, we will be taking a look at some of the other forces at some of our models of forces, such as gravity and drag and stuff like that. So we'll catch you in the next video.